All right, today we're discussing fluids. Topics include things like pressure, Bernoulli's principle, Archimedes' principle. This chapter actually talks about mechanical advantage, which we kind of introduced earlier than the book did during the static equilibrium chapter, last chapter, chapter 9. And they introduce it in a way that actually I kind of like, using the hydraulic press, which is a very nice application of all of this stuff that we learn here in the fluids chapter. So, something like lifting a really heavy car up so a mechanic can work on it, things like that. Okay, so the first section here, let's just go ahead and cover it because, not everybody always remembers this kind of stuff. And there's some interesting stuff to talk about here, and that's phases of matter. The phases that people usually learn in school, right, are the three kind of main ones that you learn are solids, liquids, and gases, right? I don't want to spend too much time on these because I think everybody pretty much learns these, chemistry in high school, even before high school these days. I mean, my baby brother is in like third grade. When he was in second grade, he was learning about phases of matter. So, it's something that nowadays is pretty common. People tend to know about them. Solids, they kind of, the atoms stay put, right? Atoms are in some kind of fixed position. They kind of stay generally where they are, right? Funny enough, you kind of get this sense that there's only one solid phase of matter, but in actuality, there are many different solid phases of matter. In fact, new ones are being discovered every single year, different crystalline structures for all kinds of different materials, and they all have unique properties. I mean, look up the Wikipedia page on ice, and there's so many different phases of ice, so many different ways the atoms, the H2O molecules, can arrange themselves. What I thought was really interesting when I first kind of was learning about that was that there are so many phases of ice that actually sink in water. But the one phase of ice that occurs at the temperatures that we have here on Earth and the pressures that we have here on Earth is the one that actually floats. So that's kind of interesting. So yeah, I want to show just real quick the Wikipedia page for the different phases of ice. So let me go ahead and do that real quick because I just think this is like really interesting. You never really get this in like your chemistry class or whatever. So can you guys see this, the wiki page? Give me a thumbs up if you can see that. It's a really interesting read. So kind of, there's a lot of stuff here just in this page. This is the page on ice here. If you want to find this, just wiki ice. And you just scroll down a little bit to this phases portion here. And you scroll down, you're like, okay, when does the list stop, right? There's ice, IH, IC, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18 and 19 actually. And then there's a couple in between like square ice and amorphous ice. So it's kind of interesting. Like if you want to just kind of, you don't have to get too detailed on the description of what these are, right? But you can just learn a little bit, for example, right here, ice 8. Where the hydrogen atoms are kind of fixed in their positions. It's formed from ice 7 by cooling it below 5 degrees Celsius at 2.1 gigapascals. That's like pressures like 1,000 times bigger than atmospheric pressure. So, I mean, actually maybe 10,000 times bigger. But yeah, so there you go. There's a little intro into that. So solids maybe is like one of the more interesting phases of matter. Let's go back over to paint now. Of course, liquids, liquids, the molecules are close together, but they tend to move pretty fast, actually. If you calculate some of the speeds of like water molecules in just your typical liquid water, right? They're moving pretty fast, like hundreds of meters per second. That's something that you would learn in the section on thermodynamics, which we're not there yet, but we can actually calculate the speeds of those molecules in a liquid. As the molecules are close together, but moving quickly, and they're moving all around, right? So you might have some molecule that you track, in water, and it might be kind of like whizzing around, and eventually it's like over here, right? It started off on this corner and it ends up over here in this corner of the container after several hours or something. Gases are like liquids. In fact, liquids and gases are sometimes referred to collectively as fluids. So here so at this stage, we should now realize that this chapter is kind of talking about liquids and gases here. So we refer to liquids and gases as fluids. At some stage, at some temperature and pressure, you cannot distinguish between a liquid and a gas. Okay, and that's called the superfluid phase of matter, and it's really just kind of gas and liquid kind of combine, the properties of both. Gases, the molecules are far apart. They're far apart compared to, maybe I should put like a little star here, close together, and then I'll put a star here, far apart. And really what I mean by that is they're close together or far apart based on the size of the molecule, right? So we all know molecules are really, really small. So since they're really small, right, far apart could mean, they're not that far apart from, like, if we were looking at them in a microscope, but far apart compared to their size, right? So the size of an atom maybe is a few nanometers, or a half a nanometer or something like that, right? So far apart might mean they're like 2 or 3 nanometers apart. So it's really not that far apart for us, but for them, molecules are far apart and moving quickly. And we talked about conservation of momentum, conservation of energy. On the atomic and molecular scale, these molecules are colliding all of the time and exchanging momenta, and all of these collisions are elastic collisions. So when we talk about, real world collisions, they tend to be inelastic, but collisions between molecules are always elastic. So that's maybe another thing. So let's go ahead and let's kind of add in our little notes here. So close together, far apart, compared to the size of the molecules or atoms. Can you guys tell I got a new mouse? Like, it's writing so well. There's no breaks. Okay, so compared to the size of molecules and atoms. That's what I mean by close together, far apart. And what was that other thing that I said? I forgot what I said already just before that.
All of the collisions are elastic?
Anybody remember what I just said before I did that?
Yeah. Can you hear me?
Oh yeah, elastic, yeah, that's right. So collisions on this scale, so collisions between molecules or atoms are always elastic in a sense, which is actually quite interesting, that that's the case, right? So we have some forces involved there, which we haven't talked about in this class yet. It's something you'll learn next semester, the electromagnetic forces, which, you know, if two molecules come and kind of get close to each other, then they repel each other, because they're electrons that are surrounding the atom. Electrons will repel other electrons. And so there's an electric force at least. Sometimes there's a magnetic force as well. But equal and opposite forces, Newton's third law applies for those electrical forces. And so you have momentum conservation, right, still, for any collisions. But the interesting thing is that the collisions between the molecules are always elastic. And so that means that energy is conserved as well. And to even take that point a little bit further, funny enough, if you take like a piece of metal, one property of metals is that they have free electrons. They're called conduction electrons, right? All the wires you've ever seen in your life are made of metal, right? Like maybe copper wires or something. They have these free electrons. And you can treat the free electrons in those wires as a gas of electrons. And actually, the collisions between those electrons and all of the different atoms along the wire actually are not elastic. So it's very kind of counterintuitive, but that gives rise to things like resistance in wires and stuff. If you're interested in like circuits and stuff like that, maybe you'll enjoy that section next semester. But yeah, so this is pretty much kind of the basics here of phases of matter. There's maybe one other, like two maybe other really interesting phases of matter that I think students like to kind of hear a little bit about. And those are plasma. And what a plasma is an ionized gas. So maybe some of you remember from your chemistry, maybe in high school, or if you took it in college, that when you ionize a molecule, you kind of write this like kind of in this notation here. So like, let's say we have sodium chloride, right, which is table salt, NaCl. Sodium chloride, table salt. The bond that is actually keeping these atoms together is not a covalent bond like oxygen gas, for example, or nitrogen gas, right? So if we had oxygen gas, it's bonded together by something called a covalent bond, which means they're sharing electrons. Sodium chloride, or your table salt, is actually bonded together by the ions, the electric force between these two ions. So sodium loses an electron to chlorine and becomes positively charged. Chlorine gains that electron from the sodium and becomes negatively charged. And then it's an electrical force of attraction. So it's like a physics kind of bond, not a chemical bond, so to speak, if you want to kind of think of it that way. But this thing right here that I've written, this Na plus right here, this is an ion. Let's change colors here so it stands out a little bit more. So this is an ion. An ion is basically a molecule or an atom that it has a charge. It has an extra electron, or it's missing an electron. So it's either positively or negatively charged. Fun fact, it was Benjamin Franklin who actually came up with that convention of positive charge or negative charge. So a plasma is an ionized gas. So typically for gases, you don't have to worry about electrical forces too much. When we look at thermodynamics later, we'll look at the ideal gas, and the ideal gas, um, the molecules are assumed to never really interact. They don't really interact. Um, you could say that they collide and they just kind of bounce off, and energy is conserved and momentum is conserved. But actually, if you have the viewpoint that the molecules just pass through one another, the physics doesn't change. So that's plasma. What are some examples of plasma? So examples. Inside those lights in the classroom, those tube lights, forgetting what they're called right now, fluorescent lights. So those fluorescent bulbs. I might be spelling this wrong, but I think it's SC, fluorescent bulbs. Let's say light bulbs. Inside the fluorescent bulb, you have a plasma there, although it's a very tame plasma. The sun is maybe the kind of big neighborhood plasma, big ball of plasma. So a lot of the molecules in the sun are actually ionized. And when you have plasmas, electric and magnetic forces become like a really big deal. So you may have heard of like things like the solar wind, the corona, these loops that form in the corona are due to like magnetic effects on the surface of the sun, or in the corona, technically. So in recent years, actually, physicists have actually made quite a big amount of progress in plasma physics. And the importance here of studying plasmas is nuclear fusion. So nuclear fusion is a way to generate energy that hasn't really been, not a lot of progress has been made on that until fairly recently. That now we have these big, basically they form a miniature sun inside of them. They're like these big superconducting magnets and all kinds of crazy stuff that maybe you might be able to talk a little bit about next semester with a little bit more knowledge. But basically, they're like these big machines that form these miniature suns. And the idea is that there's a breaking point where you put in a lot of energy to get this thing going, but if you don't get enough of it going, you don't get more energy out than you put in. And so there is a breaking point. At some point, we'll have a big enough fusion reactor where we'll put enough energy in and it will generate energy out for us. And that energy comes from the nuclear fusion. So the actual nucleus of the atoms coming together like they do in the sun. That's what keeps the sun hot. By the way, that is exactly the reason why there are no stars in the universe that are smaller than a certain size. So there is a lower limit on how big a star can be, because if it's not big enough, then it won't get energy out of its fusion process, fusing the hydrogen gas. Okay. And it's also one reason why stars die. So once they get to the point where they start forming iron atoms, they start to lose energy. So when you form iron, you don't get as much energy out as you put in. So that's when a star begins to die, is when it starts to fuse iron. And there's one more, we'll stop there for plasma. There's one more interesting one, and that is, let's go ahead and switch colors again here. That is what we'd call super solids. And I'll go ahead and put conducting here in parentheses, superconducting solids. there's been a big advancements in this area as well in recent times. So superconducting, so superconductors have zero resistance. So I mentioned resistance before for metals. So you can, metals have free electrons that can conduct electricity, and you make wires out of copper and things like that, and they have really low resistance. So we don't lose a lot of energy transporting that energy, the electricity from the power plant to your home. The less resistance, the less energy that's lost. Again, that'll be described next semester with equations and stuff. Superconductors have the property that when they're cooled down to a certain point, so they get cooled to low temperatures. And when I say low temperatures, I don't mean like you go outside and it's kind of chilly, you got to put on a jacket. We're talking like temperatures very low, like close to absolute zero for some superconductors. So absolute zero is minus 273 degrees Celsius. That's the lowest temperature you can possibly, well, it's not even a temperature that you can reach, but it's called absolute zero. You can never reach a temperature this low. Have zero resistance to transport of electricity. So I'll try and put it in layman's terms here. So zero resistance to transport of electricity. Again, this will be refined next semester. You can ask G, like, hey, we want to talk about superconductors. And I'm sure he'll be more than happy to discuss those with you guys. So superconducting cells. So superconductors. Yeah. So what is the progress that, like, what would we want to do with these, right? Well, we have to cool them to really low temperatures. That's the key. So can physicists find certain materials, certain alloys? Can we combine molecules in different ways to get what's called room temperature superconductors, which you don't have to cool them down as much to get the zero resistance property out of it? So there's a big search for what we call room temperature superconductors. And I believe right now the record room temperature superconductors, the record is like minus 100 Celsius, something like that. So record right now, something like minus, so of the order of, so approximately, I'm just giving you approximation here, something like minus 100 degrees Celsius. So we're still really far away, right? But minus 100 degrees Celsius is a lot easier to do. It's probably actually closer to minus 200 now that I'm thinking about it. Probably a lot closer to minus 200, because what I remember, the fact that I remember is that now we have superconductors which we can get them to a superconducting state using liquid nitrogen. And liquid nitrogen, if I remember correctly, is like minus 196-ish, something like that, like minus 195-ish, somewhere in that ballpark. So the current record right now is like, okay, if we have some liquid nitrogen cooling, then we can have superconducting materials. But that's the big search in physics for superconductors right now, because if we can get room temperature superconductors, then we have a whole lot more energy at our disposal, a whole lot less heating in our wires and stuff. Okay, so hopefully that was a really good, like, kind of warm up to get your brains thinking. And are there any questions about anything like that? Does anybody want to ask me any questions regarding any of that stuff? If not, we can kind of just get started on the rest of the chapter. Okay, give me a thumbs up if you're ready to go forward. Okay, so let's go ahead and get started on some descriptions of fluids. The first starting point, and we don't really have to take too much time here because I suspect a lot of us already know this, that's density, right? Density is how much mass you have per unit volume. So it's literally mass per volume. We use the symbol rho for density. And of course, mass is m, and volume we use capital V. Use capital V just to distinguish it from lowercase v, which we use for velocity, right? So it's capital V there. And, this equation is interesting because density is what we call an intrinsic property. Intrinsic property. What that means is if I have iron, all of the iron in the world, no matter how much of it I have, it has the same density. That's an intrinsic property. And these properties on the right are extrinsic properties. That means it depends on how much I have. Okay, so the idea here, intrinsic property does not depend on how much material. And then we'll just say for this one, does depend on how much. And so that might be, density, that might seem like something that's kind of boring, right? It's okay, mass versus volume. Like I've known that since I was a kid, right? Or whatever. But the fact that it is an intrinsic property has some interesting implications when you get to thermodynamics. So for example, if you want to describe a system thermodynamically, you have to describe it in such a way where there is at least one extrinsic property to tell you how much of it there is. So, there's usually like an example that's given, probably not at this level of a course, but at like a calculus-based course where you look at what's called a thermodynamic potential, and there's a way to kind of convert between these different thermodynamic potentials, and there are some of them which you might think would be a good idea to kind of write down, but it turns out they're described in terms of like 3 intrinsic properties, and so it's kind of a no-go. You have to have at least one of your quantities telling you how much of the stuff you have in your system. It's kind of like a small detail there. Let's just go ahead and jump into the next topic here, and then we'll go straight into some examples, and that is specific gravity. Okay. And specific gravity is basically like the weight of an object. How would you describe it? So probably the best way to describe it is just like the weight of an object, kind of expressed in terms of like the amount of a fluid that it displaces or something like that. I think specific gravity is not a concept that we necessarily need, but it's basically, let's go ahead and go through it. So if I want to write down the mass in terms of the density, I can do it as the density times the volume, right? Just rearrange this equation here. Then I can multiply both sides of this equation by g. And so this is the weight of the material. That is really the weight of the material itself. And then on this side, we'd have rho Vg. And I believe this quantity here is called the specific gravity. Let me double check this. Kind of forgotten myself, so. No. Oh, I'm thinking of something else. I'm jumping the gun a little bit. I'm thinking of Archimedes' principle. No, this is not called specific gravity. Sorry about that. But this indeed is the weight of the material on the left side, and so this is also the weight of the material on the right side, but expressed in terms of the density. What specific gravity is a ratio of the densities of two objects or materials. So specific gravity, yeah, it's kind of coming back to me now. So specific gravity is the ratio of the density of some material to another material. And in most cases, the ratio is taken with respect to water. Okay, so specific gravity is a ratio of densities, and in most cases, it's taken with respect to water. And the density of water in MKS units is 1,000 kilograms per meter cubed. Okay. So essentially, specific gravity is like just divide the density by 1,000. If you are working in CGS units, centimeters, grams, seconds, like you might be in chemistry, then the density of water would be 1 gram per cubic centimeter. Okay. So that's the idea there for specific gravity. Let's go ahead and get into an example here. I've already been talking quite a bit, so give me a thumbs up if you're still copying that down. Okay, we've got it. Let's go ahead and get straight into the example then. Oh, Irving, okay. Let me give you a second there. I'll write the example here while you finish that up. Okay, so just a warm-up question here. So I want you guys to work on this one solo, and hopefully you get this one pretty quick. So what is the mass of a solid sphere of iron with radius 18 centimeters? The density of iron, I was going to write Fe, but let's go ahead and write it like this. So density of iron, and then Fe is the atomic symbol for iron, right? So we'll write rho Fe there. You might see it in both ways as you're going through problems and stuff. So the density of iron is 7.8 times 10 to the third kilogram meter cubed. Kilogram per meter cubed. Okay, so go ahead and calculate this. You can go ahead and work solo on this first one because I think we all kind of know what to do here for this one. I'll give you guys like a minute to work on that. I'll get myself some water while you guys work on that. Does anybody not know what to do? Don't be scared to admit it. Just let us know so we can help. Go ahead and drag this down. Give me a thumbs up if you know what you're doing here. Give me a thumbs up if you know what you're doing. Okay. Probably some of you maybe are trying to remember the formula for the volume of a sphere. Let me just go ahead and give that to you. Volume of a sphere is 4/3 pi r cubed. Does that help? Give me a thumbs up if that helped you. Thumbs up if that helped you. You forgot the volume of the sphere. Okay, couple people. That's okay. Been a while since your geometry classes, right? So 4/3 pi r cubed. Put your answer in the chat once you get it, so we can all compare answers. Let me go ahead and get my calculator ready. All right, it's been about a minute, so let's go ahead and go over it together now. So this one shouldn't be too tough. You can just keep working if you you're almost to the answer, you know what to do, you just need a little extra time. So first thing I would do, convert that radius over to meters just to make sure we get the units right. So 0.18 meters. We can go ahead and write down the equation we're going to use. So mass equals density times volume. So density times 4/3 pi r cubed. And then now we're ready to plug in numbers because we know the density and we know the radius. So 7.8 times 10 to the third. I'll go ahead and write the units out. Kilogram per meter cubed. 4/3 times pi, and then the radius 0.18 meters quantity cubed. So we can see the meters there is going to cancel with the meters cubed down here, right? Because of the cube. And then what we get for this answer here, I'll plug it into the calculator. Go ahead and plug it into your calculator if you haven't done it yet. Times 4/3 times pi times 0.18 cubed. See what we get here. We get 190, maybe 191 if you want to round that up, and that is in units of kilograms. So that's a heavy block of iron there. That's like a block of iron that's basically like a foot in diameter, right? That's pretty big. Questions about that one before we go on to the next one? So we're just going to go straight into another example here. Give me a thumbs up if you're ready. Irving, Sammy, Leanne, Denelise, Jew. Want some extra time? Ask questions if you have questions. Don't forget to ask if you need some help. We can go ahead and do the next one in groups. So I'll give you guys a couple minutes, work in groups on it, and I'll come around. Next example here. And this is going to be a simple one as well. Actually, you know what? Let's work on this next one solo because actually it's a really simple one, and then for the next one we'll do the groups. Okay. So what is the specific gravity? Actually, let's change it a little bit. What is the density of alcohol if its specific gravity is, we'll use the abbreviation SG for specific gravity, is 0.79. That's a unitless quantity. Specific gravity is unitless. Okay, so what is the density of alcohol? To be more specific, some of you probably have taken chemistry. You know that this word alcohol applies to many different molecular structures or molecular compositions here. So specifically, we're talking about ethanol. Which is C2H6O. There's a better way to write that. C2H5OH. Okay. All right, does everybody have the answer now? Give me a thumbs up if you got the answer. One person. Let me remind you, specific gravity is the ratio of the density of the substance you're interested in to the density of water. The density of water is 1,000 kilogram meters per meter cubed in our units. So how do we get the density of alcohol? Multiply the specific gravity by 1,000, so 0.79 times 1,000 kilogram per meter cubed. So about 790 kilogram per meter cubed. A slightly better answer would be 789 kilogram per meter cubed. I looked it up on Google just a second ago. Because in the book, so I actually looked it up because the book gave the specific gravity, but it didn't tell you of which kind of alcohol. So I was like, okay. So I looked up at a table and found the one that matched what they were doing. It was ethanol, so I gave you that information. So there are other kinds of alcohols, so you can look up their, they're going to have their own densities and stuff. Any questions about that one? Those were two straightforward examples. So are we all warmed up now? Give me a thumbs up if we're nice and warmed up now. Now we're going to start getting to a couple, maybe a little bit more complicated material for this chapter now. So let's make sure we're squared away on this. Question for you guys. Will iron sink or float in water? Yes or no? Or maybe? Does iron sink or float in water? I want to see some answers in the chat. Come on, let's get some interaction here in this. Does iron sink or float in water? Or maybe it depends. Maybe the answer depends. Sink, sink, sink. Density is higher than water. I think sink, sink. Everybody thinks sink. Okay, that's good. That's a very intuitive answer, right? Sammy says depends. Denelise, sink. I think it's natural when we think about this. We think, okay, iron, more dense, it's going to sink in water, right? How do we then explain that the Navy has these massive boats made of iron and they float on the ocean? They don't sink, right? They carry all kinds of these jets. They take off from the Navy, the aircraft carrier ships. They're made of metal, right? They're all made of iron. So how is it that it floats? That is the question that we will answer today. And yes, you are correct in thinking that it has to do with buoyancy. So it is a misconception to think about density as a determining factor in whether something sinks or floats. Okay, so I notice some of you know that it buoyancy, right? So some of you know buoyancy, but when I ask if it sinks, you say perhaps iron is more dense and therefore it will sink. But that is not the case. It's always buoyancy. So I want you to remember that. So always think about buoyancy to determine if something sinks or floats. Okay? Never density. Never think about density. Okay? All right, so let's go ahead and get into some of these topics now. So the first thing that we're going to talk about is pressure. And pressure is going to be a recurring theme as we kind of move forward here. It's kind of like the major concept in this section, in this chapter. So pressure in fluids. Pressure has a really simple definition. It's just force per unit area. And we use the letter capital P for pressure. So force per unit area. That's pressure. That's just a definition there. That's not, we're not deriving an equation here. It's just a definition. Okay. And I mentioned before in the chapter on static equilibrium, the dimensions of pressure, the SI units, rather, I should say, the SI units of pressure are Newton per meter squared, but we call that a Pascal, PA, named after the scientist Pascal. How do you say his name? Blaise Pascal or something like that, or Blaise Pascal. I don't know how to say his name. Here, I can write it for you though. Maybe one of you knows how to say that. But there it is. And some common units you might see for pressure, kind of like English units rather than SI units, are PSI. So PSI is the English unit, which is pounds per square inch. So the English units are pounds per square inch, PSI. And I mentioned last time the pressure in your tires, they tell you air them up to 36 PSI. That's actually an overpressure. That's a pressure above atmospheric pressure. And atmospheric pressure is about 14.5 PSI. So really your tire, the absolute pressure inside of your tires is something like 50 PSI. So yeah, so an example there of like the English unit. So it's a common unit that you'll see, especially in the United States. Okay, so let's go ahead and calculate, just get into an example right away here. So here's an example. I'll just pull this one from the book here. And this is going to be the amount of pressure exerted on the bottom of your feet, okay? So the example here is you have a 60 kilogram person. Okay, on 2 feet, right? Let's just write the word 2 since we're not going to use that 2 for any calculations. You ever notice that whenever you see numbers in like a problem statement, the numbers that are written out as like the spelling of the number are the ones you don't use to calculate typically. So on 2 feet of let's try and word this. How does the book word this? Cover an area of, yeah, I guess that's okay. So on 2 feet, which cover an area A equals 500 square centimeters. Measuring the area that your feet cover is probably like something you could do, like approximate pretty easily. Just treat your foot as a rectangle, right? Just measure the length and measure the width. Just treat it as if it's like a rectangular foot. You could probably figure that out pretty easily. So we're calculating the pressure of just standing on 2 feet. So this is part A. Then what we want to do is compare that with the pressure on 1 foot. Okay, so calculate the force on the feet. What's going to be the force on the feet? Before I put you guys in groups, what's going to be the force on the feet? Let's see some answers in chat. What are the forces acting in this problem here? What's the force that you actually feel on your feet? Is that your weight? Is that a normal force? Is that some sort of electrical force? Technically, 2 of those are the correct answer. Let's see some chats. Normal force, I like it. Normal force. Who agrees with normal force? mg is another one. Do we feel forces of gravity? Do we feel gravitational forces? Denali says yes. Christine says we feel normal force. Christiana says no. We don't feel gravitational forces, right? That's why we feel weightless. If we're an astronaut in outer space, we still have that gravitational force pulling on us, but we don't feel it. We only feel the normal force when we're in contact with something. So we feel our weight on our feet when we're standing on Earth, because that normal force is equal to our weight. So we only feel the normal force. So I'm going to go ahead and put you guys in groups now. Just to explain, let's go through the question one more time. We have a 60 kilogram person on 2 feet, which cover an area of 500 square centimeters. What is the pressure on the feet, on the 2 feet? We're going to calculate that as the normal force over the area. The normal force over the area. I'm going to put you guys in groups now. Excuse me. So we'll do 2 to 3 per group. Oh, wow. Okay, let's go ahead. I think these groups are fine. Let's go ahead and open it up. There we go. Your rooms are open. Go ahead and join your rooms. I'll be around shortly. Yeah, let's go to the rooms. Hello, how are we doing in here? Chat, hello, good. Evelyn, Liliana, Evelyn. Oh no, Evelyn, you just, Denalise, I mean.
I'm good.
You're good, okay. Are we talking? Are we sharing our answers? Make sure we're on the same page here.
Not yet. We just all kind of got in here when
Liliana,
you
you
got
there?
here. Yeah, I'm here.
Can't hear you if you're talking. Maybe it's me. Oh. Hello? Can you guys talk again?
Hello, can you hear me?
Yeah, it was me. I didn't even have my speakers on this whole time.
Oh no.
I don't know if anybody tried to say anything to me during class.
I think one student, but it was just for one time.
Oh, who was it?
Either Christina or Christine. I always get them
Christine?
mixed up.
Oh, okay. Yeah, I didn't even have my speakers on for some reason. Didn't notice.
Yeah.
Okay, so you're doing okay in this room?
Yeah.
All right, I'll
Yeah.
go to the next one. Hello. Well, that was loud and weird. How are you guys doing in here? Matthew, Sammy, you talking in chat? A little confused? Okay. What is the confusion? So pressure is force over area. Maybe I can share the screen again here. So pressure is force over area. So the force here is going to be the normal force. But the normal force is going to be equal to the weight, right? That's the catch. So it seems almost like I'm, maybe like I'm trying to confuse people, but really I'm trying to get you to understand like a common misconception, right? You don't feel gravitational forces, you just feel the normal force. But when you're standing on a level surface, the normal force is equal to the weight, right? And the weight is the gravitational force. So the normal force here is mg. Does that make sense? Does that kind of clear it up? Yeah, exactly. 60. Oh, no. Normal force is the weight. So mg, right? So 60 times 9.8, right? You're going to divide by that 500, but make sure you convert, right? You need to convert that. It's centimeters squared. You want to convert that to meters squared. So, it's 100 centimeters per meter. Don't forget to square that conversion, right? All right, any questions from, who's the other person in the group? I can't see. Oh, Sammy. There we go. Any questions for me, Sammy? Both stuck there. Okay, yeah. So just before I leave, what would you do for part B? What would we do for part B? If we're on 1 foot, half the area. Exactly, right? That's the idea. And you can really actually feel that, right? Stand up in your room right now. I mean, even as like kids even know this, right? You stand on one leg, you can feel that on that foot, right? Double the pressure. All right, so I'm gonna head to the next group now. Hello. I don't know why it keeps saying that now. That's weird. Did you guys hear that? Like it says recording in progress.
Yeah, but it always says that.
It always says. I've only ever heard that recently. Somebody pointed out to me that I had my speakers off earlier, and you said something to me during class. I didn't hear what you said.
I was just reminding you because you lost your train of thought in the lecture. I was just reminding you where we were at.
Oh, so it looked like I was ignoring you or something.
No, I just figured because your speakers were off before, so I was like, oh, he probably has his speakers off again.
Did I do that before? I don't remember.
Yeah, we were all trying to like get your attention to like record and
Okay, yeah. Okay, so how are we doing in here? Ju and Leanne, are you two doing okay? Or I see Christine, you put an answer in the chat already.
Yeah, I kind of figured it out. It was just we had a minor like conversion
Yeah, you got to convert
mistake,
centimeters
so
squared.
then yeah,
I
but
mean,
we're good now.
technically, I mean, it's not wrong. You just have, excuse me, you just have a different set of units, right? So as long as you've done force over area, and the force is the normal force, but the normal force is equal to the weight. I know it sounds like maybe it's adding a little bit of confusion, but that's kind of like a common misconception, is that students think that they can feel the gravitational force, but of course that doesn't explain weightlessness that astronauts feel, right, in space. So if you're an astronaut in space, you can't feel the gravitational force, but it's definitely there. You only feel the normal force on your feet, which is equal to your weight when you're standing on the surface of the earth. So yeah, so Ju, how about you? How are you doing? Oh, you said yes in the chat. I don't remember what I asked. So are you good on this one? Okay. All right, so I'll go to the next group then. There's one more group to check on here. Okay, I'm here. So, how you two doing? Irving, Christiana, how are we doing? Doing okay. Good sign.
Yeah,
Irving, you're doing okay?
yeah. So it would be mass times g divided by 500, but then it wouldn't be 500. It would be 0.05
Yeah, you
meters
got to
square.
convert it. Yep, exactly. You got to convert it. I 0.05. Yeah, I think that sounds right. I think
Yeah.
that sounds right. Yeah. So you know what you're doing then. Good. So you got. What would you do for part B?
Oh, I haven't gotten to that part.
Just give me an idea. Like, what would you if you're going from 2 feet to 1 feet? What would you do?
Would you divide the 500 by 2?
Yeah, exactly. You're on 1 foot now. So
Yeah.
you divide the area by 2. Exactly. Okay. All right. I'm going to close the rooms here in like 30 to a minute, something like that. Okay.
Okay.
I'll make sure everybody has some time to finish their thoughts. Oh, I was muted that whole time. Okay, well, wasn't lecturing, so that. And we will get the next example ready. Okay, let's go ahead and close the rooms now. Everyone some time to come back. Just a couple more people. Room's about to close. Everybody should be coming in now. All right, give me a thumbs up if that was enough time. Did we have enough time to kind of finish that off? If you just got part A, that's probably good enough. I think most of you were able to tell me what to do for part B. Okay, so I'll go ahead and share screen and we'll go ahead and cover this example real quick and then we'll go to the next topic and do another example. Okay, so what we want to do here is kind of what I've already written here, but I'll go ahead and write it again. It is going to be that the normal force divided by the area is going to be the pressure on the 2 feet. Okay, and that normal force is going to be equal to the weight of the person, provided that they are standing on a level surface. In fact, if they were standing on like a hill or something like that, then actually our answer would be slightly different. Excuse me. So mg divided by that area. So 60 kilograms times the famous 9.8 meters per second squared divided by, now this 500 centimeters squared needs to be converted. You can multiply that by 1 meter per 100 centimeters. We have to square that piece. So just multiply that by a conversion factor. What we ultimately end up with here, I'll go ahead and punch it into the calculator here, 60 times 9.8. When I push divide, I always make sure I put some extra parentheses here. So 500 times 1 divided by 100, and I want to square that bit, and then close off my parentheses for the other division there, and I end up with 11.8 thousand, 11.8 kilopascals. Let's write it like that. 11.8 kilopascals. Okay. Is that what everybody else was getting? Let's see. Give me a thumbs up if that's what you were getting. So 11.8 times 10 to the third, or 11,760, I think was the answer there if you multiply those numbers. Irving, Leanne, is that what you two got? Irving, good, okay. Leanne, did you get that answer too? Yeah, okay. All right, so you guys tell me in the chat, what do I do for part B? Some of us didn't have quite enough time to finish off part B, I don't think. So what do we do for part B? Maybe somebody who hasn't said something in chat yet. What do we do for part B when we go for 2 feet to 1 foot? What do we do for 2 feet to 1 foot? That was meant to be a question. Okay, Leanne says same but half the area. I like that. Irving, divide by 250 centimeters squared. Should be centimeters squared there, but yes, that's correct. So that's the right idea. Okay, so for 1 foot, it's exactly the same, except we just replace this with 250 centimeters squared. In other words, half the area. Let's see what happens. I mean, we're going from 1 foot to, from 2 feet to 1 foot. Let's see what happens here if we were to just write it in equation form. It's the same normal force, right? But now we plug in area over 2, right? This just flips up and multiplies. So we have twice the pressure that we had before. So why calculate again if we don't have to, right? This tells us we're going to get twice as much. So our answer is going to be 23.6 kilopascals. Again, 11,760 pascals is fine. 23,520 pascals. These are probably the answers you get in your calculator. Those are correct answers. But we want to write it in scientific notation as kilopascals or times 10 to the third, right? Okay, any questions on that one? Any questions? We are going to introduce a new topic, but related to what we're doing here, so not entirely new. Okay, so let's go ahead and go to the next topic then. So I already have an example ready down there, but we're not quite ready for that example yet. So we need to introduce the idea of a pressure change in a fluid as you go deeper and deeper into the fluid. So simple concept, suppose we have a tank of water, and you can look up better pictures in your book. It's actually like for my other classes, it's kind of easy for me to like grab figures from the textbook. Like if I click a figure, it gives me like a nice like thing I can copy paste like directly into Paint. But I guess because this is a little bit of an older book, I can't do that as easily here. I have to like screenshot it and then like delete all the extra crap. So, and maybe something to look into next time I teach a class, and maybe pick a newer book or something. So here's the water. So just suppose water, it could be any fluid though. And of course, if we were to go down, let's make this a little bit more three-dimensional, because it's actually important that this is three-dimensional here. This. Maybe I should just use this line feature here. This. Okay, something like this. This one. And this one. And over here, just trying to get a nice picture for us here so we can really distinguish certain things. Kind of wish I didn't do the blue lines like that, but I think it's fine. Okay, so we want to take a look at now, and I'll use another color here, maybe pink. Want to take a look at a box of this fluid here. So I want to take a look at a box which is at a depth h into the fluid. Okay, so imagine maybe you're in the ocean and you dive down into the ocean a depth h. You know, it could be a couple meters, could be a couple, feet, right? If it was a couple miles, you'd have to be in a submarine, right? So here we have an area A for the bottom face of that rectangular shape there, and then a height or a depth of h. Okay. Now, if I am down here, if I am at this location here, at the point, let's call it maybe, what's a good name for a point here? I don't want to use P, let's use Q here, right? Your math class, you point P, point Q, that kind of thing. So at point Q, which is at a depth of h, we have a pressure. We have the weight of all of this fluid on top of our head, right? All of the weight above us, all of the weight of the fluid above us is pushing down on us, right? The gravitational force is pulling all of that fluid on top of us down onto us. And of course, there's normal forces associated with that from the weight of the fluid acting on our heads, right? Our shoulders and all over our body. And so there's a pressure associated with that, okay? What is that pressure? Well, we can start by writing down that the pressure is force over area. And the force that's acting on us is the weight of the fluid divided by that area. And the weight of the fluid, as we saw before, was rho v times g. So this right here is the mass, right? Right, or m. Okay. And then, of course, multiply mass times the gravitational acceleration, and you get the weight. Again, divided by area. But what is the volume here of this fluid that is above us? Well, it's the same as the height times that area. Volume of a rectangular shape like this, or a cube, right, is side times side times side. So it's mass times area times the height times the gravitational acceleration divided by A. And you might say, well, wait a minute, we're just talking about like a single point here. Well, yeah, you can imagine that this is a very small area. So the area, let's say, of your head, the top of your head is at that point Q. And that A is just the area of that cross section of the top of your skull, right? And you could take that argument even further. You could use a little bit of calculus and say, okay, we're looking at when A is like infinitesimally small, like A is almost zero, right? And in both cases, we're going to get the same answer here. So what happens is, because we divide by the area here in the definition of the pressure, then the A's cancel out. Those are the same A's there. And what we see, to finish it off maybe in red here, is that the pressure at depth H is equal to mgh. Okay. Oh, sorry. No, it's not mgh. It's rho. It's rho gh. Did anybody catch that? Anybody catch that? I switched rho over to m there. That was a mistake. Change that in your notes. Okay, it should say rho gh. As soon as I wrote mgh, I was like, wait a minute, that's potential energy. No, it's rho gh. Rho gh. Make sure you got that correct in your notes, okay? Make sure you got that correct in your notes. Change this term right here to rho. Sorry about that. Okay, so the pressure at depth H is rho gh. Okay, and that pressure is in addition to whatever the ambient pressure is, P0. Okay, that is in addition to whatever the ambient pressure is at 0. So include this, include P0 if you need absolute pressure. So if you dive down into the ocean, not only is the weight of the water acting on top of your head, but so is the weight of the air above the water. All of that is acting on you. So there's an ambient pressure that we talk about called atmospheric pressure. And so P0 in a lot of cases will just be the atmospheric pressure. It's just going to be a constant value, you know, that it'll just be something that I give you on a test, right? It's about 100 kilopascals. So include P0 if you need absolute pressure. Okay, maybe let's make it a complete sentence here. So capital I, include P0 if you need absolute pressure. Ignore P0 if you just want gauge pressure. Ignore P0 if you want gauge pressure. Can you guys read this? I'm trying to kind of fit it here. If you want gauge pressure. So for example, when you're at the gas station, you're airing up your tires and you're airing them up, and then you're trying to check the pressure to see if you've got it right. The meter that you're reading the pressure from is a gauge reading. So it's not telling you the absolute pressure. It's telling you the pressure above atmospheric pressure. That's gauge pressure. Okay. All right, so in the case of diving into the ocean, the pressure would need to be atmospheric pressure plus this pressure, which depends on H here, how deep you go. The deeper you go, the more pressure there's going to be. But if you were to carry with you a gauge pressure measuring device, if you were to dive down, if you were a scuba diver, you dive down in the ocean with a gauge pressure meter, then the gauge pressure meter would only measure this part right here. Okay. So this would be what the gauge pressure for a scuba dive depth H into the ocean. Okay. So any questions about that before we jump into this example here? So this example is directly related to this idea of the deeper you go or the higher up you are, right? There's a pressure associated with that change in height. Okay. So that's another thing here. And this is going to be relevant for this example. So let me just go ahead and write it here. You can think of a change in pressure now, which would be like a final pressure minus an initial pressure, which would be equal to, if we call this the absolute pressure here, the absolute pressure is P0, whatever the ambient pressure is, which is usually atmospheric pressure, plus the pressure that you experience because you're diving deeper into the ocean, right? Well, then that would simply be P0 plus rho. I kind of maybe, what I wrote here maybe was a little bit confusing actually, now that I'm looking at it again. The pressure at depth H is rho GH. That's an equation, but I put this extra bit here plus P0. I did not mean to imply that P0 plus P at a depth H is equal to rho GH. So make sure in your notes, that might have been a little bit confusing, sorry about that. Make sure that this thing here in box is a separate equation. This is the pressure simply due to the weight of like a liquid, like water, like you dive into the ocean. So we have, for our delta P, it's rho GH final, P0 plus rho GH final, minus P0 plus rho GH initial, and that's going to be equal to rho G delta H. And so delta P is equal to rho G delta H. So this P0 term here is constant. So whenever we take a delta, it's going to just cancel out because you're going to have something like this here. P0 minus P0. So that's the idea there. So when we do a delta, then we don't have to remember, okay, am I talking about absolute pressure or am I talking about gauge pressure? If you have a delta P, it doesn't matter. Okay, so change in pressure is the same for absolute or gauge pressure. So it works for both of them. It's the same for absolute. Let's use the word and here. Change in pressure is the same for absolute and gauge pressure. Okay. And now we should be well equipped enough to take a look at this example problem. So once you're done copying this bit down here, the delta P equals rho G delta H, and this little note on the side, then go ahead and start copying down this example right here. And that's the next example that we're going to work on. And I'll put you guys in groups again, I think, for this one. Go ahead and give me a thumbs up when you're done copying. Not quite everyone. I think maybe that was half of us. Make sure you get it copied down, because once we go into the break rooms, right, you can't see the screen anymore. So one thing I think like a decent number of my students in my my physics 222 class do is they just like take a picture of it. That way they can see everything that was written on the page before I put them in the breakout room. So maybe that'll help you if you want to copy it, if you want to get it, you know, exact, and then you can copy it in later. But okay, let's go ahead and form the rooms again. Did you guys like the rooms last time? Were those good rooms? We can go ahead and do the same rooms again. Doesn't seem like there's any objection. So there you go. They're open, and I'll come in again and check on progress and help you get started on it if you need some help. So go ahead and join your rooms. Irving, are you there? Still copying it down? Okay, pause the recording again. Here? How are we doing here?
We're doing good.
Yeah, okay. What are we thinking for the setup here on this one? Just give me a little bit about how you're going to set it up.
So we were just going to use delta P equals lowercase, I forget what the actual Greek letter is, but like the
Rho.
lowercase p looking one.
Yeah, rho.
Rho times
Yeah.
G times delta H.
Okay, good. Does everybody agree with that? Is there any particular trick to this one?
No, it's pretty simple as far as I can tell.
Good. Okay, so I'm going to go to the next room. Hello. How are we doing over here? Is this one straightforward, or do we need some help here? Matthew, Sammy. Would it be 30? Yeah, rho, that looks pretty good to me. That's delta P equals rho G delta H, so sounds good to me. There's no tricks to this one then? How about you, Sammy? Does that make sense? Yeah, okay, good. All right, I'll go to the next room. Still working with that, yeah.
H. So final minus initial, which is 0 minus 30, because it starts. Does it start at 30?
You know, that's a fantastic question. I feel like it doesn't really matter because it's really just like the difference in the height, but um, that's a logical thought. I don't think actually you can have a negative change in pressure. That's possible.
Professor, is the height negative or positive?
Yeah, so I mean it's a good question to think about.
Mhm.
It says specifically the surface of the water in a storage tank is 30 meters above a water faucet in the kitchen of a house. Calculate the difference in water pressure between the faucet and the surface of the water in the tank. So the pressure is certainly higher at the bottom than at the top. There is no water pressure at the top. Does that answer the question?
Not really.
So if the pressure is bigger at the bottom,
hmm
that's your final, right? And your initial is 0.
Okay.
So so that's, I guess that's maybe something I could have emphasized a little bit more. The lower you go, the bigger the pressure. That means more positive.
Okay,
So
so I'm in the wrong here. Okay, cool.
its depth is how H is measured. So positive numbers are measured downward.
That makes sense. Okay. Yeah, that makes sense. Okay, so I got the right number, but just wrong sign. Cool.
Well, you're doing good. How about you, Ju? Any questions? Doing good. All right. Sounds good. Christine, you got it?
Yeah, I think so. Is it your birthday today?
Yeah, it is.
Happy birthday.
Thank you. All right, I'll go to the next room.
Hmm.
Hello, how are we doing in here?
Good.
Good. We understand this one?
Yeah, you just multiply the 1000 kg over m3 times 9.8 times 30.
Mm-hmm. Yep.
Okay. It would be 294,000.
Is the pressure, so question, is the pressure greater at the bottom or at the top?
Uh
If I dive deeper into the ocean, does the pressure go up or down?
up.
It goes up. Okay.
Yeah.
All right. I'm going to close the rooms pretty soon.
Okay.
Close the rooms here in a second. Broadcast a message first. About 1 minute. Yeah, I'll get the next thing ready. Excuse me. Okay, let's go ahead and close the rooms now. Welcome back. Just wait for everybody else. Share screen here. Clean this up. Oops. Delta H. All right, is that everybody? I think that's everybody. Yeah, 11 people. Okay. So let's go ahead and tackle this problem real quick. I was asked a good question by one of the groups, and that was, should the pressure be negative? Should the change in pressure be negative? The answer is no, because pressure decreases as you go down. So H is measured positive as you go further down. So that's maybe not something we're used to seeing. We're used to seeing, you know, like negative Y values, right? When you go down. But in this case, the further you go down, the greater the pressure. So our answer here should be positive. So in order to get that answer, our delta P should be rho G H final minus rho G H initial, like this. And our initial H we can take to be 0. And we take our final H to be the 30 meters of depth that we go down the faucet, down to the faucet, from the water tank down to the faucet. So if we look at it in that case, water has a density of 1,000 kilograms per meter cubed. G is 9.8 meters per second squared. And the final depth here, 30 meters. And what do we get out of this? We get roughly 300,000, right? Roughly 300 kilopascals. I'm just approximating G to be 10 here, so it's like 300 times 1,000. Okay, so any questions about that one? Or I think everybody was pretty good on that one, to be honest. Not really many questions there. This is about 3 times atmospheric pressure, which is what we're going to talk about next. Okay, so about 3 times atmospheric pressure there. Question for you guys. If the water pressure in the tank, if the tank was completely full of water, there was no air inside the tank at all, would water even come out of the faucet if the pressure wasn't greater than atmospheric pressure? Question for you guys. So would water come out of the faucet if the water pressure was less than atmospheric pressure due to the air? Okay. Would water come out of the faucet if the water pressure was less than atmospheric pressure due to the air? So that's a question for you guys. Yes, no? Does it depend? Right? Let me know. So give your answers in chat. Finally, we have some brave souls answering no. Okay, let's go. Let's talk about it. The correct answer is no. Let's understand why. Suppose I have a pipe here, okay? There's a pressure from the inside of the pipe due to the water. You can think of that pressure as a force because we have an area here. And there is then a force on the other end due to the air pressure. So we have air pressure. And again, as long as we have a well-defined area, we can talk about force. So these pressures give rise to forces, and then those forces we can apply Newton's laws to understand what's going to happen there. So if we want water to come out of the faucet, we have to at least have pressure equal to the air pressure. But the pressure better be bigger if we want to force that water to come out, right? So the fact we have 3 times the atmospheric pressure there, that's probably a good thing. That means we can actually get some water to come out. Okay. All right, so the next topic here is atmospheric pressure and gauge pressure. Let me go ahead and move this up. And the idea here is exactly the same as what we just talked about for fluid pressure, or up here, pressure at a certain height. Although things get a little bit more complicated because probably, as you guys know, water is what we call an incompressible fluid, right? So what does that mean, incompressible? It means if you put very large forces on water, like if you try to squeeze the water really tight, try to make it shrink, try to shrink its volume, it doesn't change much. It'll change a very, very small amount when you apply very large pressures. So we call it incompressible, so it's hard to change the volume. Contrary to liquids, which tend to be somewhat incompressible, gases are very compressible. So the air in the atmosphere has a variable density depending on the height. So air in the atmosphere has variable density. Oops. And its density is actually exponential. So something like e to the minus h, roughly speaking. So the higher up, and in this case, that h really is a height above the surface of the earth. So as we go higher and higher, the air is less dense. And down here towards the surface of Earth, the air is as dense as it's going to get. So air in the atmosphere has a variable density, and I'll put exponential. If we were in a calculus-based class, maybe we could prove that. We could actually write down the equation. We could solve a little equation and show that, but it's it's a differential equation, so a little bit more than we should do in this class. So the air in the atmosphere has a variable density. So the equation delta P equals rho G delta H doesn't work for the atmospheric pressure because this equation assumes constant density. So this equation assumes, and to be very specific about what I mean by constant density, I'll say this equation assumes density does not change with height or depth. Okay. And like I said, the density of the atmosphere is variable. It's exponential. It's something like e to the minus and then how far above the surface you are. So it's more dense close to the surface and less dense further away, like further above the surface. And since the density is exponential, the pressure will also be exponential in the same way. And so we cannot use this linear relationship here between delta P and delta H. It's an exponential relationship. So what we do is we typically perform our experiments at the surface of the Earth, right? In the laboratory, we're at the surface of the Earth. Maybe if we're up in a mountain, like some school up in the mountains and we're in the lab working on some stuff, we might have to actually measure the atmospheric pressure there and maybe make slight adjustments to the values that we use, to the constants that we use for the atmospheric pressure so that we get the correct answer. But for us, we're pretty much at the surface of the Earth. And so we're just going to use this standard value for 1 atmosphere at the surface, right? So we're not really high up in the mountains, so that should be good enough for us. So again, it still is the total weight of all of the air above us. So it's still the total weight. It's just that in order to get that weight, we have to have a variable density that we sum up as we increase in height to get the total weight of a column of air that's above us. But it's still the same concept. It's the total weight of air above divided by the area. Okay. And again, that area could be like the top of your head, right? It's acting all over the surface of the Earth. So actually, so a nice thing about air pressure actually is you can take the total mass, or not mass, but the total weight of all of the air on Earth and divide by the surface area of the Earth, and you get this value for the air pressure at the surface, which essentially it's the same pressure almost everywhere. Even if you go up like 100 meters or so, it's still roughly the same air pressure. And that has to do with the fact that the density is exponential. Only once you get to really high above the surface do you start to notice drastic changes in the air pressure. You have to go up about, I want to say last time I checked, about 95% of all of the air in the atmosphere is within 10 kilometers of the surface. And the total atmosphere of the Earth extends up to about 87 kilometers. A lot of people like to just say 100 kilometers. But I believe these days people are talking about kind of refining what we mean by the atmosphere. And so they've given this kind of value of 87 kilometers for certain reasons that I'm not fully, I don't fully understand myself because I haven't really looked into it much. But yeah, so if you want to say like the atmosphere goes up about 100 kilometers, that's pretty good. And you want to calculate the total weight of all of that air in the atmosphere and divide by the surface area of the Earth. Just take the surface of a sphere, right, with a given radius for the radius of the Earth, 6,400 kilometers. And that's going to give you the air pressure. So we call this the PATM, or atmospheric pressure. And this value is constant. Everywhere that we measured on the surface, if we change to a small area, if we change to a big area, if we have a massive skyscraper, or if we're just a small little person, looking up at the massive skyscraper, we're all experiencing the same air pressure. All of that weight is distributed evenly amongst the entire surface of the Earth. And this value, when we calculate it at the surface, comes out to 1.0, and is it 01? Yeah, 01. The book gives 1.013 times 10 to the 5 pascals, or 101 kilopascals if you're good with just 3 sig figs. Okay, 101 kilopascals. And some people actually, I think in chemistry nowadays, I think they're taking exactly 100 kilopascals for the atmospheric pressure. Don't quote me on that though. I'm not 100% sure on that. But that is, or maybe that's what they define to be the standard pressure actually. So there's STP, right? Standard temperature and pressure. So maybe standard pressure, I think, might be 100 kilopascals. So it's not quite equal to 1 atmosphere. But anyways, that's the next line that comes after this 101 kilopascals. This is by definition 1 atmosphere, 1 ATM. And that is a unit of pressure there. So that's like a defined unit, 1 atmosphere. So sometimes we'll talk about pressure in atmospheres. There's one other little thing of note here, and that is 1 bar. That is another unit of pressure. 1 bar is another unit defined in terms of pascals. It's actually 1.000 times 10. I imagine these zeros are repeating, so they mean exactly 1 times 10 to the 5th Newton meter squared, or pascals. Okay. So 1 bar is basically 1 atmosphere, just a little bit less than 1 atmosphere. So yeah, I think, yeah, so maybe what it is in chemistry, I think, is they use 1 bar as the standard pressure. So this is standard pressure. Okay, and then, there's things like standard temperature, right? And standard temperature is 0 degrees Celsius, right? Or 273 Kelvin. Any questions about that air pressure there? So it's the weight of all of the air in the atmosphere acting on the entire surface of the Earth. And depending on your depth in that fluid, the air is a fluid, right? The gases are fluids. The pressure may be different. So if we go up at the top of Mount Everest, right, we're like 8,000 some meters above the surface, way less pressure up there than down here at the surface. Okay, so I don't see anybody asking any questions, so we'll go ahead now and we'll talk about gauge pressure. So gauge pressure we already kind of talked about. I introduced it already, but let's now kind of refine what it is here. So gauge pressure is the amount of pressure above atmospheric pressure. So when we talk about absolute pressure, and actually I'll subscript absolute so that we know exactly what we're talking about here. The absolute pressure is any ambient pressure that might be there in your system, maybe due to air pressure, plus some sort of gauge pressure. Okay, so P0 here is typically going to be the atmospheric pressure. So atmospheric pressure, which is, as we just discussed, 1.01 times 10 to the 5th pascals. And then this could be any number of different things. Like, for example, this could be, like a rho G H type of thing, right? So it could be some fluid pressure, right? Like for water. So let's say maybe like water pressure. Maybe water pressure. It could be some other force acting over some area. It doesn't have to be a pressure due to the weight of a fluid. I could, for example, in like a piston, right? Like in a car engine or something. I mean, it doesn't even have to be in a car engine. I could just hold a piston in my hand, right? So I could just hold a piston in my hand, which maybe looks something like this. And I could just grab this thing and I could just push down on it, right? I could just push down on the piston. I could just apply a force. And of course, there's some area here, right? And so I'm applying a pressure, right? So there may be some air inside that piston that I'm compressing by applying a force, right? So maybe I should put a vector sign here and then put applied. It's an applied force. So over here, we can put that this force is applied. Okay. And, that's kind of our options, really. So pressure is defined as a force over an area. So if you can't write it down in terms of maybe some sort of weight of a fluid type of pressure, or you've dived down into the ocean, right? So the weight of all the fluid above you divided, the density of the fluid times the gravity times the depth is going to give you the fluid pressure, right? Or maybe you have some forces acting on an object that are external forces. It's not to do with some weight of a fluid. Those would be maybe some applied forces. Then those are your only options there for the gauge pressure. So that's pretty much what it is. So if you are using a gauge to measure pressure, so this is measured by, and I think there's a name for a device which measures gauge pressure. What is it called? Name of device that measures gauge pressure, just so I can give it to you. It's not in the book, and I forgot what it's called. Okay, so there is a word I've never actually seen this one before. Manometer. But actually, it seems to be telling me that they just call them pressure gauges. And if you want to measure absolute pressure, these are usually called barometers. And let me just go ahead and double check that just to be sure here. I think that's good. Yeah. You may come across some other names for those things, but that's good for us. So again, the same tire example I gave before. So gauge pressure is like measuring the pressure in your tires. Okay, let's go ahead and take a look at a particular example in the book, which is really kind of like a conceptual question. I think this would maybe be like a good question to have some discussion about. So I'll actually just type up the question real quick here. So the title of the question here is, and this may be a very familiar situation for most of us, especially when we were kids, and that's when your finger holds water in a straw. Okay, so let's try to understand this kind of simple idea, like why we can pick the water up when we hold our finger over the straw, right? So you insert a straw of length L into a tall glass of water. You place your finger over the top of the straw, capturing some air above the water, but preventing any additional air from getting in or out. And then you lift the straw from the water. You find that the straw retains most of the water. Does the air in the space between your fingers, or your finger, and the top of the water have a pressure P that is greater than, let's maybe go bold here, greater than, equal to, or less than the atmospheric pressure P0 or PATM outside the straw. Okay, so this is like a conceptual, like discussion question. So I will invite you to discuss, and I'll put you in rooms again. But this time, let me make sure that I put you guys in rooms where like at least one of you has a mic, so there's kind of a little bit of talking that can be involved here. So can you let me know in chat if you do not have a mic? So tell me in chat if you do not have a mic. So let me know in chat if you do not have a microphone. Okay, so I'll try to match you three with people who do not have, or so who do have microphones. Christiana, Sammy, and Jew. Okay, so now I'll form the groups again. So recreate the rooms, recreate. So let's see, where's Jew? Okay, Jew there, that's fine. Christiana doesn't. Let's see, where are you at? Okay, I think that'll be fine. And then Sammy, yeah, that should be fine too. So I think all three of you are with people who do have mics, so there'd be a little bit of some actual discussions there. So if you don't have a mic though, obviously you can type a little bit in chat to kind of contribute to the discussion, okay? So I'd like to see everybody kind of discussing everything. We'll spend maybe like 2 minutes on this one, and then we'll talk about it as a class and we'll move forward. So the rooms are open. Go ahead and join your rooms and begin the discussion after you've kind of copied it down. So I know I wrote a lot there, so maybe take a picture if you're still copying, so that way you can start up with the discussion right away. Are you there, Leanne? Okay. Okay, we'll go ahead and pause the recording. Okay, so everyone's here. So I'm sharing screen. I drew a little picture for one group. So this is the setup here. We have a straw. We put our finger over the top of the straw, and what happens is the water has to be supported by something, right? And it's supported by atmospheric pressure, but there's also air at the top of the straw. And since there's air at the top of the straw, the pressure in that air must be either greater than, equal to, or less than the atmospheric pressure, so that the water there will not fall out of the straw. So let's hear from some of the groups here. So maybe Christiana, what's your, oh no, you don't have a microphone. How about Matthew? Why don't you give us what your group kind of figured out about this one?
I wasn't sure personally, but someone else, or they were discussing that they think it was lighter. It'd be lighter on the inside.
Lighter as in the pressure of the air inside is less than atmospheric?
Yeah, sorry, it's less than, yeah.
Got you. Okay, good. How about Liliana? I know you have a microphone.
Yeah, we were talking about how we were thinking maybe it's higher because like I specifically brought up the water tank example a little bit ago, how you mentioned that the pressure had to be higher for the water to flow. So therefore it makes sense that if the water's not flowing, or sorry, I said higher originally, I meant less. Because if the water's not flowing, the pressure inside is probably less than, just an opposite to that water tank example.
Okay, all right. Maybe one more. How about Leanne?
Oh, I was in the same group as Matthew, so
Okay. So you got this one then. How about
yeah, I said less than.
okay? Who else has a mic? Irving. You had a mic, right?
Yeah, we also said less than.
Okay. All right. So everybody is getting the correct answer, it seems. So let's understand mathematically how it works. The answer is less than. The pressure inside of the little container region here between the water and your finger has to be less than atmospheric pressure by a certain amount. And that amount is just enough so that the force acting at the surface here is different by an amount equal to the weight of the water. So let's put it in force terms so that it really ties into what we've done before, right? So we have this water which has a force on it due to atmospheric pressure. And that force is basically the pressure of the atmosphere times the cross-sectional area of the straw. Then we have the weight of the water, right? So this is the force, which is just the weight of the water. So W for weight. Maybe I should put Fg. So it's a gravitational force when it's weight, right? So Fg is the weight of the water. Maybe I should put a vector sign. I should actually probably get rid of the vector signs, honestly, because we're talking about pressure, and pressure is not a vector. So if you were wondering about that, there's your answer. Pressure is not a vector. I made that vector a little bit too long there. And then we have the downward pressure here, and this is the pressure of the air, which must be less than atmospheric pressure. Oh, sorry. I'm looking at forces, not pressures. So this is the force on that cross section, which is the pressure of the air there times the same area, the same cross-sectional area of the straw there. Okay, and we know that P air must be less than P ATM just based on this free body diagram here, right? So if we were to really get down into the details here, we should sum up the forces. And since we are in static equilibrium, right? There's no fluid coming out of the straw. We're in static equilibrium. The sum of the forces should be equal to 0. And of course, the y direction here, we can take this direction to be positive. So that means we have the force of the atmosphere minus the force due to the air pressure at the top minus the weight of the water. That should be equal to 0, and we can see that the pressure, the atmospheric pressure, times the area of the straw, the cross-sectional area of the straw, should be equal to the pressure in the air there times the cross-sectional area of the straw plus the weight of the water. Okay, so we could take the atmospheric pressure times the cross-sectional area of that straw and then just subtract the weight of the water, and that would be our answer there for this term here. So maybe we should write it that way one more way. So let's go ahead and do that. So subtract the weight of the water, right? Subtract the weight of the water, both sides. And what we end up with is that the pressure due to the air, if I divide by the area of the straw, is going to be equal to the atmospheric pressure, area of the straw cancels, minus the weight of the water divided by the area of the straw. Let me know if I did too many algebra steps in a row there without spelling it out. Give me a thumbs up if that algebra made sense, or should I show an extra step there? I kind of skipped like 2 steps there. Not a whole lot of thumbs up, so maybe I should show like another step here. So when I do this, I get PATM, area of the straw, minus the weight of the water, and that's equal to the pressure of the air at the top times the area of the straw. And then divide everything by the area of the straw. Right, and so the area of the straw on the right-hand side cancels out. And then I just changed the order here. I just wrote this one on the left side. So in this particular term here, this one cancels, and then the area of the straw just divides the area of the water there, right? So this is our answer that we end up with. And so we can actually calculate exactly how much the the pressure is inside of the straw. As a matter of fact, we could take it one step further. We could calculate the exact pressure based on how high the water is in the straw as well, right? The weight of the water is its mass times the gravitational acceleration. And we saw before, that means mass is density times volume times g, right? Keep the g there. So this is mass right here. And the volume there is simply rho, the cross-sectional area of the straw, times the, let's call it y. Y is how much water there is in the straw, like the height of the water in the straw, basically. So we're not using the same symbol h, times g. And now you can see even the area of the straw cancels out in the weight of the water. So the pressure of air is the atmospheric pressure, that 101 kilopascals, minus rho g and then y. And again, the meaning of y is how high water is above, how high water is above the bottom opening. Does that make sense? So So we can actually calculate exactly what the pressure is. This is the pressure right here as a function of y. So depending on how much water we have in that straw, we'll know the pressure of the air above it. So that's pretty interesting. So we've taken like a children's game of, you know, like sucking the water into the straw and turned it into a physics problem. Okay. So any questions about that? Again, just a reminder, since we haven't seen it that much, atmospheric pressure is 1.01 times 10 to the 5 pascals, or 101 kilopascals. Okay. So we'll go ahead and go to the next topic here, since there are no questions. And that's going to be Pascal's principle. Let's maybe create here like a custom color here. We're introducing new colors now. So Pascal's principle. Okay. And what Pascal's principle is it's a statement about pressure in a fluid. So if you have a fluid which is confined to some container and you apply an external pressure to that fluid, then the pressure inside the fluid everywhere at every point increases by the same amount. Okay. So what it means is, let's go ahead and write it in words actually. So an external pressure applied to a, what should we call it? Confined fluid. Confined fluid. So an external pressure applied to a confined fluid increases the pressure by the same amount at every point in the fluid. By the same amount at every point in the fluid. Okay. So what does that mean? That means that no matter how far you dive down into the ocean, or no matter where you go in the ocean, the atmospheric pressure of the air above the ocean is felt by you. You're feeling that pressure. That's kind of like a nice way of thinking about it. You dive real deep down into the ocean and you're feeling the pressure of the water, but you're also still feeling the pressure of the air above the water, right? So that's the idea. So if you, and the same thing applies if you were to have a tube, let's say like this. Let's say you have a tube here. A U-shaped tube like this. Okay. And these two areas here don't necessarily even have to be the same. You could have like some A1 and A2 here. Let's make A1 this new blue color here. Do you guys like this new blue color? Actually looks pretty nice. Okay, so A1 and A2 here, and this container is filled with water. So we have water all throughout this container. So there's water everywhere. You know what, maybe a better way to make the water there would be to do this. Hopefully this doesn't ruin the whole screen. Okay, there we go. That works, yeah. And this is the water here. So if I were to, let's say, apply a force here, like let's say I apply a force, let's call it F1, then the pressure would be F1 over A1, right? I apply a force at this surface here, A1. So the pressure that I'm applying to that surface is F1 divided by A1. Okay. Pascal's principle says if an external pressure is applied to a confined fluid, certainly we have an external pressure here due to force F1, and we definitely have a confined fluid. The fluid is confined to this closed pipe here, right? Then that fluid's pressure is going to increase by the same amount everywhere. So the pressure here, oh yeah, I'm on the green already. So the pressure here is going to be equal to, so the final pressure is going to, okay, that's a little bit hard to read, huh? Maybe something brighter. So there we go. That's pretty, you guys can read that, right? So the final pressure is going to be the initial pressure plus F1 over A1 at this level right here. Okay, well, we said that if we were to go down a depth h, that the pressure would change, right? So if we were to go down a depth h here, the pressure would increase by an amount proportional to the change in height, right? Rho g delta h. But that pressure would increase by the same amount, F1 over A1, compared to what it was before the external pressure was applied. So the pressure here will be, so at this point, maybe we'll use another shade of yellow to show that these are different here. So kind of more of like an orangish yellow now. So the final pressure here is going to be the initial pressure plus, and let's say, I should say final pressure prime and initial pressure prime, because they are different. If I go down H, my pressure certainly goes up, but that's not what we're saying here. We're saying that if we apply an external pressure, then the pressure everywhere will increase by the same amount. So that means that this pressure down here will also increase by an amount F1 over A1. And we could take that one step further, and we could say that P final prime is equal to P initial unprimed plus rho g h to account for the change in height plus F1 over A1. Okay. So notice now I can maybe use pink here. This P and this P are the same, but this P, that's prime. This one is not the same. Do you guys see that? That's the difference there. So this is Pascal's principle right here. This part. So these two being the same. I shouldn't use red. Let me use another color. Let's create a new color here. Yeah, that looks pretty good. Okay, this right here is Pascal's principle. This part right here. Excuse me. Okay, that's Pascal's principle right there. Now, there's a really, really, really nice application of Pascal's principle, which I've taken the time here to carefully walk through this piece here, because now the next logical question to ask, and I hope you're thinking the same thing, is, okay, the pressure here at the yellow line is now increased by F1 over A1, and the pressure here at this kind of yellowish orangish line has increased by a factor F1 over A1. Now we obviously need to go up this way and see what happens at this surface now, which we have not looked at, right? So that is the next logical thing to do there. And this brown is not quite yellow enough, so let's make it maybe a little bit more yellow here. There we go. So now we want to know what happens here at this surface. Okay. Well, the pressure there, according to Pascal's principle, is whatever it was before plus an amount F1 over A1. Okay, so the pressure here and pressure here. And by the way, if it's at the same height like this, if these two are at the same height, then their pressure is the same. P initial plus F1 over A1. But now the area that that pressure acts on is not the same area. It's A2, it's not A1. So as a consequence of this, there is a different force on this area, call it F2, and F2 is, oh, no, sorry, not a vector, not a vector. We know the direction already, so I don't want to write vectors in equations because pressures are not vectors. F2 is A2 times F1 over A1. Okay, why is that the case? Well, look here at this expression. Okay. We started with some initial pressure. That initial pressure, we don't care what it is. The initial pressure has a force. Yes, there's a force there on A2 due to the initial pressure. But this system is in static equilibrium. So when I apply the force F1, I take the system out of static equilibrium because I apply a force. Something's got to give. So when I apply the force F1 on the left side, I get a force on the right side, F2. And the initial pressure doesn't factor into that force because it was in static equilibrium before I applied F1. So the only piece that I care about here is the change in pressure. And the change in pressure will get me the force F2 because F2 is the additional amount of force on the surface A2 when I applied F1 to the surface A1. And F1 is an additional amount of force that I've applied to surface A1. So here, if I instead write in terms of deltas, so delta P is F1 over A1. And so if I take delta P times A2, then I end up with F1 over A1 times A2. And that right there is the physics of a hydraulic pump. That's why you take your car to the mechanic, they drive it up on top of this platform, and they're able to just lift your car just with ease all the way up, 10 feet in the air, right? So they can work on it from below or whatever. That's the idea right there. So if I have a large A1 and I apply a force to a large A1, then what happens is if A1 is large, then I have a small pressure on the left side, right? So if I apply a force on a large area, I'm going to get a small pressure. But that small pressure is translated over to the other surface where A2 is. And so if I make, depending on what I make A2, I can make that force really big, or I can make it really small. If I make A2 bigger than A1, I make that force really big. If I make A2 smaller than A1, then I make that force really small. Okay, so the idea then would be to have A1 be small well, let's be really specific here. So hydraulic press okay. So for a hydraulic press, we want to apply a force F to an area A1 which is much smaller than A2. And the lifting force F2 I should have said maybe apply a force F1 to an area A1. Sorry about that. I missed a little subscript of a 1 there. So apply a force F1 to an area A1, which is much smaller than A2. And the lifting force F2 will be much bigger than F1. How much bigger will it be? By the way, this is an extremely important result right here. This is absolutely insane, this result. This tells us that a baby can get on top of a hydraulic press and lift a car. That's essentially what we're saying here. We can choose the area A1 and we can choose the area A2. We can fill this thing with an incompressible fluid and we can have a baby smacking a rubber hammer on A1 and eventually lift a car up a certain height, however high you want, given enough time, okay? So it's absolutely crazy that Pascal's principle exists. It's a real thing. This is how hydraulic presses work, but energy always has to be conserved. So if you're gonna lift a car, you have to put in enough energy to lift the car. So it's gonna take time, right? It's going to take a lot of time. Okay, well, of course, we can have machines do this for us and make things go faster, right? And that's kind of what happens at the mechanic. All right, so how much bigger? Again, F2 is going to be equal to A2 over A1 times F1, and you may recognize this expression here where we have some force on this side and some force over here which was applied. So this is our output, this is our input. Whenever we have input times something equals output, that means that this something right here is the mechanical advantage. So this is mechanical advantage. So we called that before MA. And we can write it as A2 over A1. Or if you take a look at the equation, we could technically also write it as F2 divided by F1. And we always take F1 here to be the applied force or the input. So it's always output divided by input. Okay. Questions about that? Or is that making sense? Give me a thumbs up if that's making sense and you're ready to move on. Okay, good number of you. So let's go ahead and press forward now. So the next thing that I kind of want to talk about here is buoyancy and Archimedes principle. And I think that we should, there isn't a great example in the book here for mechanical advantage, but obviously I kind of was talking about one, right? Like lifting a car with you know, much lower force. So we could probably create an example, but with only like 20 minutes left, I think it's really important we cover buoyancy and Archimedes principle. So if you'll bear with me here, I'm going to keep talking for like another 20 minutes probably. Maybe we can get an example in at the end for Archimedes principle. So let's go ahead and take a look at it. So Archimedes principle, there's a famous anecdote. You know, I don't know if it's ever been shown that it was indeed true or not, that it actually happened, but you know, there's no reason to really believe it didn't happen, I don't think. But basically, there was an anecdote about Archimedes where the king wanted to know if the crown was made of pure gold, right? Because, you know, kings are greedy, right? It's got to be pure gold. And Archimedes was tasked with figuring out if the crown really was pure gold or not. And so how did he do that, right? That's like Archimedes was alive like 2,000 plus years ago. So the way he did it was he knew something about submerging objects in liquid. So what he knew was, and I'm going to go ahead and type this to save a little bit of time. So Archimedes knew that if he submerged an object with a volume V into a fluid, like water, the amount of water that is displaced or has to move out of the way is the same volume V as the object. Okay. So I'll read that off one more time. That was kind of quick. You guys are probably copying it. Archimedes Whoops, I put an apostrophe there. There shouldn't be an apostrophe there. So Archimedes knew that if he submerged an object with a volume V into a fluid like water, then the amount of water that is displaced or has to move out of the way is the same volume V as the object. We can get a nice picture for this too. So let's do it. So here is a bunch of water, and the water is this high. Let's say, you know, the volume of the, let's actually try and make it like a three-dimensional diagram here. So since we're talking about volumes, so let's go ahead and do like straight lines like this, straight lines like this. That's close enough. We do like a curvy one here, so it's like a cylinder here. Okay, Archimedes knew that if he put some water in this tub here, and I think the anecdote talks about how he used a bathtub or something to do this, to show that the crown was like gold or whatever. So we have this much water here in this column, and we can note that the volume of the water initially is the initial volume. Okay. Then what happens is we take this tub and we drop a gold crown into the tub. Let's see if I can maybe use this function right here to. Wow, okay, that worked better than I thought it was going to. Okay. So we take this crown and we submerge it into water here like this. And once the crown goes into the water, like this, the volume, and of course gold, a gold crown like this, which is solid gold, it's gonna sink to the bottom. The buoyant force is not gonna be large enough to support the weight of the crown. So this crown will sink, but I've just kind of drawn it like this. Maybe we can move it down to the bottom. We can do something like this maybe and move it to the bottom just to really, there it is, it's at the bottom now. When the crown is in the water, the volume has changed. We're now at V final, okay? And the volume of the crown is equal to delta V, the change in volume of the fluid, and in particular of the liquid. I mean, I guess I should just say water since Archimedes used water here. So since we're talking about Archimedes. So the change in volume of the water is equal to the volume of the crown. And of course, Archimedes was a smart guy. He knew about density and volumes and you know, like the weight of objects and stuff like that, right? He did not know about mass, but weight is good enough in this case. And so he was able to figure out based on the density of gold whether or not the crown was pure gold or not. Okay. So that's the fun little anecdote about Archimedes. What is the real physics now that we can do? Well, knowing this fact here, you might suspect that the water that you push out of the way for the crown will push back on the crown itself, right? Newton's third law. So Newton's third law. If the crown pushes water away, well, we should just say if the crown pushes on water, then the water pushes on the crown, right? So if that's the case, then let's quantify the amount that the water pushes on the crown. Let's try to do it all in this one figure here because it'll save us a little bit of time here. So there's pressure in the fluid. At the top of the crown, there's a pressure at the top. At the bottom of the crown, there is a pressure at the bottom. And the difference in pressure is given by the density of the fluid, of the water, times the gravitational acceleration, times the difference in height, right? So if the crown is submerged in water, the difference in pressure between the top and bottom part of the crown is given in terms of the height, so to speak, of the crown. So delta H here is simply delta H for the crown, right? And it is these two forces that are due to the difference in pressure at the top and at the bottom of the object, which gives the buoyant force. Notice that the pressure at the bottom is always bigger than the pressure at the top. So there is always a buoyant force that goes against the weight of an object. Okay? There is always a buoyant force that goes against the weight of an object. Okay? So this gives rise to some force F at the top. All right, so let's look at the bottom force first since that one's bigger. So F at the bottom minus F at the top is equal to the buoyant force FB. Okay, FB for short, the buoyant force, okay? And we can clearly see here that if I multiply this equation, if I go from pressure to force, delta F would be equal to delta P times A, right? Where A is the area of the bottom part of the crown and the top part of the crown. Of course, a crown is jagged and has many sides and things, but if we were to look at a very small piece of the, like in a calculus sense, like differential size, like a very small delta, then we would be able to show that it doesn't matter that the crown has all these crooks and crannies in it. And we would multiply delta P by A, and delta P is rho G delta H times A, and this piece right here is the volume, the volume of the fluid that is displaced by the crown. So this equation really tells us, the buoyant force FB is equal to the difference in forces between the top and bottom, which is the same as the difference in pressures from the top and bottom times an area of the cross section. And of course, the area of the cross section times delta H is of the volume of a piece of the crown. And if we were to sum up all the little pieces of volume, the little heights of the crown, we would get the total volume of the crown. And that is rho GV. And everything here has to do with the fluid. So fluid, this is all parameters for the fluid. It's density of the fluid. It's volume of the fluid that is displaced, okay? So I should say volume of displaced fluid. Okay. And of course, Archimedes knew that the volume of the displaced fluid was the same as the volume of the crown. Okay? But it is nice to remember that the buoyant force on the crown is only given in terms of parameters for the fluid. Okay, so it's a nice way to remember what's going on here. Buoyant force on the crown only in terms of things for the fluid. So density of the fluid and volume displaced of the fluid. Okay. All right. Let's try to do an example. Or we can write in words really quick. Actually, let me type this out in words real quick. So there's an important statement about buoyant force. So the buoyant force on any object is equal to the weight of the fluid displaced by that object. Okay. Remember that rho times v is equal to mass. And of course, this is the mass of the fluid. Okay, so for Archimedes, that's water. So maybe we could write one more equation sign here. So it's the mass times gravity. So it's the weight of the fluid. Any questions about that? I'll give you some time to copy that down. Let's try to get in one example here. We got 6 minutes left. We should try and get in an example, yeah? So while you guys are copying that down, let me get that next example ready. Oops. Okay, you guys ready for this example? Let's go through this one together since we don't have much time. Okay, so maybe I'll ask you little questions here and there to kind of help us get through it. Okay, so let me read the problem while you copy it down. A 70-kilogram ancient statue lies at the bottom of the sea. Its volume is 3.0 times 10 to the 4 centimeters cubed. How much force is needed to lift it without acceleration? How much force is needed to lift it without acceleration? Well, it's some kind of statue, right, at the bottom of the sea. So here's the sea right here. And then we have the sand at the bottom, right? There's the statue. What are the forces involved? Obviously, we have the weight of the statue, right? The weight of the statue. What else? What's another force that we have here? Of course, we would have a normal force because this statue is at the bottom of the sea, right? It's not accelerating, so there must be a normal force there to balance kind of the other forces involved. But if we were to lift this object a little bit up off the ground, then there wouldn't be a normal force anymore. So that's what we want to do. We want to assume there's no normal force here. Who can tell me what's another force acting on this object? Maybe a force we just talked about?
The buoyant force?
Buoyant force? Doesn't that sound like we definitely have a buoyant force here? Right? We have a statue at the bottom of the sea, right? It's submerged in a fluid. So if the statue wasn't here, there would be liquid where the statue is, right? And so this statue must have displaced some of the fluid, right? Whenever you stick something into something else, like if you put some ice in your glass of water, the water level rises, right? Even though the ice doesn't sink all the way, right? It only sinks in a little bit. It sinks in a little bit and then we say it floats. There's a buoyant force there. So here the statue, the buoyant force isn't big enough to allow this thing to float, but there is a buoyant force, but it's not quite big enough. Okay, the buoyant force. Okay, if we want to lift this thing without acceleration, what does that mean? What can I say about the acceleration? Acceleration equals what? What does acceleration equal if we have no acceleration?
0?
0. It's not a trick question. It's going to be 0. So that means if we sum the forces, we should get 0, right? So sum the forces and get 0. Well, I know the weight of the statue is bigger than the buoyant force, right? I know that mg is bigger than FB. So I have to apply an additional force here. Maybe it's this much. This is the force that I need to lift. So this is, let's call it the lifting force. Okay. So here then the summation of forces would be, okay, let's take up to be positive. So the lift force plus the buoyant force minus the weight, which is mg for the statue. Since we're talking about the weight of the statue here, that's got to be equal to 0. The buoyant force is going to be all in terms of the fluid. So density of the fluid times the gravitational acceleration times the volume, and the volume of fluid that is displaced, is equal to the volume of the statue. Okay, so the volume of the fluid displaced is equal to the volume of the statue. All right, so that's everything that we need there to solve for the lifting force. So the lifting force, let's try and finish this off in the next 30 seconds here, and we can end, is mg minus rho gv. So it's the difference between the weight of the object and the weight of the fluid that it displaced. Remember, this is weight of fluid displaced. And of course, this is the weight of the statue. It always helps to kind of write these things out a couple times when you're first going through this, because common mistakes for this type of problem is to just use the wrong density, right? So maybe they tell you it's an iron statue, and so you go and look up the density of iron and you plug in the density of iron when you should have just plugged in the density of water, right? So you got to remember it's the fluid stuff on the rho GV, and it's the weight of the statue. And so we're ready to plug in numbers at this point. So let's go ahead and go over to the calculator. Maybe let's write out a few more steps here. So m 70 kilograms for the statue, gravitational acceleration 9.8 meters per second squared, minus density of water is 1,000 kilogram per meters cubed. Gravitational acceleration again, 9.8 meters per second squared times, and then we need the volume of the statue because it's the same as the volume of displaced fluid in this case, because the statue is fully submerged in water. If we were talking about a boat, then the volume of fluid displaced would not be the full volume of the boat, right? That wouldn't be the case. But in this case, since the statue is fully submerged, it is going to be the case. So the volume displaced, we have to do a little conversion here. So 3 times 10 to the 4 cubic centimeters. We better convert that. We better put 100 centimeters for 1 meter, and we better cube this thing. And if we cube this down here is 10 to the 2. So really we're just dividing by 1,000,000. So our answer is really going to be 0.03 cubic meters. All right, we're ready to go over to the calculator. So in parentheses over here on the right-hand side, 0.03 meters cubed. Okay, let's calculate. I got Wolfram Alpha over here ready to go. And this is where we'll end here. So 70 times 9.8. Go ahead and calculate along with me. 70 kilograms times 9.8 meters per second squared. That's the weight of the statue minus density of water, 1,000, times 9.8 gravitational acceleration times 0.03. Close off my parentheses there. And I get 392. And of course, my units here are newtons. Okay, so let's go ahead and end things there. Feel free to ask me any questions now. So does anybody have any questions for me? Does that example make sense? Anything unclear about what we covered? That was Archimedes Principle. So what all did we cover today? We covered phases of matter, covered pressure, right? Covered specific gravity, covered Pascal's principle, covered mechanical advantage, and we covered Archimedes principle. So there are a couple topics that we weren't able to cover. And so it'll be up to you to kind of go through those yourselves and understand those. Those topics are fluids in motion, or flow rate and equation of continuity. So mass continuity. That's section 10.8. And then we have Bernoulli's principle, or Bernoulli's equation, which is 10.9, which is basically conservation of energy for fluids. So it really shouldn't be too much of a difficulty if you're really thinking about like energy and stuff. I think it's pretty straightforward. And then the last section there, 10.10, is like applications of Bernoulli's principle to things like airplanes or like blood flow, stuff like that. So maybe those are interesting as well. And that's pretty much everything that we need to cover. So we won't do too much with viscosity. Okay, so viscosity is section 10-11. I think I put maybe 1 or 2 problems on the homework assignments for viscosity, but I tried to pick ones that were very simple, like not really like if you read the section on viscosity, it's pretty short. All of these sections like 10.10 and beyond are all kind of short sections. So, all right, I'm gonna go ahead and stop recording now, and